afternoon, but it's not the last talk of the workshop. So we have one talk tomorrow, Friday, at 10:40 a.m. It's the last talk of the workshop, but not the least. So this is tomorrow's talk is by Katie Craig. So please do come back tomorrow for the last talk. So for today, let me introduce the last speaker in the afternoon is Aaron Palmer from UBC. He's going to talk to us about information in mean field control. So please, Aaron.
Okay, thank you, Jeff, and thank you the other organizers for inviting me to speak here, and everyone for attending. It's been a great workshop so far. So I'm going to be talking today about the role of information in mean field control, or more generally in sort of these high dimensional optimization problems, which goes to sort of some of a very similar problem that as in our last talk, where we're going to look at like a controlled Markov process with partial information, and looking at the asymptotic limits as the number of agents in the number of states in the Markov process goes to infinity. So to give a little overview of the talk, I wanted to mention that yeah, it's a project I've been working on by myself, and I'm gonna have a preprint available soon, but I haven't really shared it with many people, so I'm excited to share it today. So to begin the talk, I'm going to talk about some of the applications and results in partial information stochastic control theory and related problems, some of the motivation for the work that I'm doing. And then I'll formulate the more specific problem of a controlled Markov process with partial information and give some illustrating example. And the analysis will break down into two parts. So the first part is going to be to look at the mean field limit and see that the role of the information doesn't play a role in the mean field limit. And this is something that's been recognized in a lot of the mean field type problems, is the dependence on the information sort of vanishes. However, in the second part of the analysis, we're going to look at the fluctuations about the mean field limit. And in looking at these fluctuations, we can understand a little bit better about what is the role of information for these problems. And to conclude, I'm going to have some discussion on this sort of more complex problem, which I would say has short range interactions and a lot more complicated phenomena that can occur. So to begin, so the result that's really sort of fundamental to the approach that I'm going to be taking in this talk is this work by Kalman on the linear filtering, which is solving a Bayesian inference problem with sort of linear dynamics and Gaussian noise. And so this famous paper from the 60s has almost 35,000 citations, been used everywhere. And the main concept is called a Kalman filter, which is going to take our time series of noisy observations and partial observations of the process and produce an estimate of the state of the process. And one of the first applications of this idea was in the Apollo program. And so, of course, in the Apollo program, they landed a shuttle on the moon, and the shuttle was controlled by the astronauts, but Kalman filtering was used in the instruments to give the astronauts an accurate estimate of the trajectory and orientation of the shuttle. And it was essential for being able to land safely. And so associated to this Kalman filtering procedure is a stochastic control problem, which is called the linear quadratic Gaussian control problem. And it'll come up as a major technique later in the talk, and it's solved by this procedure of Kalman filtering combined with dynamic programming. And this is now a standard technique in many areas, including like autopilot and algorithmic trading or high frequency trading. So just a little more motivation for why we're studying this problem. So thinking about it from an economic perspective, we're in this information age And so it's obvious that businesses are making a lot of decisions and valuing very highly the information about their customers. And looking at the role of information in economic theory can go back to some early work by von Mises, which is a kind of critique of socialism, where he kind of showed that that a centralized agency cannot make very good decisions about how to allocate resources if they don't have good information about the needs of the people and the needs of the industry. And however, after that work, mathematical economics developed essentially with the assumptions of perfect information. So I'm kind of talking about the work of Kantorovich and Nash and Pareto, who all developed this more mathematical theory of economics, but really assuming that the perfect information was known about all of these things. And then came another really influential work, which sort of was showing a sort of flaw in now free market economics, and showing that inefficiencies can arise due to imperfect information. And so if we look at the title of this paper, Informational Imperfections in the Capital Market and Macroeconomic Fluctuations, it kind of parallels the main idea I want to say in my talk, which is that the role of information shows up in the fluctuations about the mean behavior. And it's actually a little bit different here. When they talked about fluctuations, they were talking about periodic deviations from the mean, while I was talking about stochastic deviations from the mean. But there's some relations. And so since then, information has played a major role in economics. So information economics sort of focuses on the microeconomic problems of games and auctions and the role of the information available to the different players. And econometrics focuses on the building of macroeconomic models using observational data. And in this talk, I want to talk about sort of what's bridging the gap between the microscopic and the macroscopic pictures. So here's some related works on the partial information control problem. So in the 80s, there was a lot of work on developing a general approach, which was done using this sort of stochastic Pontryagin maximum principle. And this approach has been applied also to mean field type problems with partial information, as well as a lot of the linear quadratic Gaussian type mean field problems, which can be solved. And then, so recently there's been some work about the fluctuations about the mean field. So here's a couple papers. The first paper is looking at the fluctuations about a continuous state space model, which is involving stochastic PDEs. It's a little bit complicated. What I'm going to be talking about is more closely related to the second paper by Chechen and Polino, where they look at the fluctuations about a finite state mean field game problem, and they can describe the fluctuations using the master equation sort of techniques. And so in this talk, so both those works we're using sort of the full information problem. So I want to focus here on this talk about the fluctuations about the mean field in the partial information problem, which will use a linear quadratic Gaussian approximation. And I also want to have a focus sort of on a practical computational approach, whereas in some of these other approaches to studying the fluctuations, they're using these systems of PDEs or even infinite dimensional PDEs. And here I'm just going to be using ODE systems to approach this problem. And it's going to make it a little more practical to solve in high dimensions. And so please interrupt me if you have any more. I'm sorry, is this, I'm not sure what happened there. Is it back?
I think we dropped or something for a second.
Okay.
But please go on. Yeah, sorry.
Okay, 1 second. Let me. How do we do this? Okay, can everyone see the slides again and hear me?
Yes, we can see them. Yeah.
Okay, great, thank you. Okay, so to start out, to describe the problem, I'm going to describe it through an example, and it's going to be an example of an epidemic model, which is on a lot of people's minds at the moment. And sort of the most basic example where we're going to have a collection of n individuals, which are grouped into 3 states, which are the individuals susceptible to being infected, the infected or infectious individuals, and those that have already been infected and recovered. And so for an individual, you can think of this as a 3-state Markov process where the transition from being the susceptible state to the infected state is happening at a rate that's proportional to infection rate alpha and the total number of infected individuals. And then the rate that you transition to be recovered is a constant gamma. And so we're going to look at this model and have the infection rate alpha be controlled by say, social distancing policies. And so so there's 2 ways to think about this model, either in terms of the individuals, in which case you would have a Markov process with 3 to the n states, or if you group them together in terms of the sigma variables, which I'll be doing, which counts the number of individuals, you would have sort of a system of 3 times n states. And there you can compute the expected drift, and the expected drift, right, is what we're going to use to describe the mean behavior. And it has this sort of familiar form of this SIR model where the change in the susceptible and infected people is nonlinear in the sigma variables. So right, the individual rates, say, to become affected is alpha times sigma 1, but when you have sigma 0, number of individuals, these rates add up to have the overall rate of having the jumps, the transitions from, say, sigma 0 to sigma 0 minus 1 over n, having rate actually n times alpha sigma 0 sigma 1. And so we're going to look at this in a minimizing the expectation of some cost, which is going to balance sort of the social cost or economic cost of reducing alpha. So we're going to look at something that has like a minus log alpha cost. So the cost of reducing alpha increases as it gets closer and closer to alpha equals 0, and also the cost of having infections in the population. And so, right, we really want to understand this, though, in this context of partial information. So the way we're going to involve information in this problem is through modeling sort of the positive tests. And the positive tests, upsilon, are going to be generated by the infected individuals at a constant rate nu, say. And so the problem, the partial information problem, is to minimize the total expected cost over a finite time horizon, where the control policy is a function of the history of all of these observations of positive tests. And so I probably said that this was a Markov process, but actually when the control is a function of the history of these tests, it's non-Markovian, and that introduces a lot of difficulties in solving this problem. Difficulties in just doing the Bayesian inference to figure out the distribution of the states, as well as not being able to apply the dynamic programming principle. So here's a figure. So this SIR model, controlled SIR model, was kind of loosely based on a work I did on optimal control SIR models over the summer. And here I'm just plotting just the number of infected individuals. And we're going to see, so I think this had 10,000 individuals, and we started out with 100 infected. And we're going to do some like strong social distancing, some lockdown to get to drive the number of infected individuals down. And in the second graph in the red, we see the number of positive tests per day that are being observed. And we're going to base our control policy alpha on these positive tests. And so we'll see later in this talk how we come up with this. This is an approximate optimal policy for this problem. So going back to the more general problem I want to consider. So we have a finite state Markov process with n individuals in L states, say. And so in the last example, the number of states was 3, but I'd want to consider it also when it's a large number of states. And we're going to look at these empirical or compartmental measures, which just count the number of agents in each state. And we're going to suppose that the Markov transition matrices are controlled and are given as some function of both alpha and this empirical measure of states. And so I'm not going to say exactly what all this transition rate matrices are, but from them you can get this sort of expected drift, which will just be a function of the empirical measure and the control, and also an infinitesimal covariance of this jump process, which, because you're looking at sort of jumps of 1 over n that are occurring at a rate n, the covariance actually ends up with a factor of 1 over n. And so the cost, yeah, is just an expectation of a running cost and terminal cost as functions of the empirical measure and the control. And right, the observation process is this parallel process upsilon, which is very similar, being generated, right? Some Markov transition matrix that's depending, in this case, only on the state sigma. And we're restricting to the control policies that are the functions of the history of the observations. So the first thing I want to look at is what is the mean field variant of this problem. So in the mean field, we're going to approximate our state variable sigma as some deterministic trajectory S. And similarly, the control and observations will be approximated by some deterministic trajectory. And so we're going to assume that the initial condition that's given is converging in distribution here to some constant S0, and the observations start at 0. And so the mean field control problem actually just reduces to this ordinary optimal control problem, where we have the right-hand side of the state equation is given by the expected drifts, and the cost is now just this standard optimal control cost. And so of course now you can see that there are always deterministic solutions to this mean field problem that don't use any of the observational process U. And so to state that sort of as a theorem, so I'm going to suppose under the condition that the mean field problem has a unique minimizer, then the minimizers of the n agent problem converge in distribution to the deterministic trajectory that minimizes the mean field optimal control problem. And furthermore, the solution of the mean field control provides an approximately optimal policy for the stochastic n player problem. And right, so in this case, this doesn't use any of the information. So it's definitely admissible control policy. And to the leading order asymptotics in n, it's the best thing to do. And to solve for the S star A star, we can just apply this sort of standard optimal control Pontryagin maximum principle. And when we solve the maximum principle, we're computing a co-state variable P is sort of a generalized momentum, and it can be interpreted as giving the first variation of the cost with respect to the state variable. And I just want to highlight in this theorem, there's no role played by the observational process or the information. And this has been an observation in a lot of mean field games in various contexts. So now I want to go to kind of the main part of the analysis, which is to describe the fluctuations of this finite player process. So the fluctuations are going to be coming from this sort of functional central limit theorem, where you look at the right. So you look at the difference, the deviation from the mean multiplied by the square root of n, and we'll see that that will converge to a Gaussian process S for the state with zero mean. And so right, if you just think about it in terms of the normal central limit theorem, right, you converge to a Gaussian which has mean 0, and the covariance matrix is given by the covariance of the finite player problems. And so it's very similar here, except we have to take into account that these are determined by this optimization. And so when we understand the fluctuations, we can understand the asymptotics of the cost function. So the n player cost that will have, well, so there's a sort of first variation that's just given from the solution to the mean field problem, right? Using this co-state variable p star. And that corresponds to this sort of deviation of the expected initial condition as sort of 1 over n or zeta over n. And then we're going to have a second term, which is what we'll focus on here, which is coming from the fluctuations about the mean field. And this term is now going to involve a sort of second order expansion of the cost function and the fluctuations of our state control and observational variables. And if you notice, right, there's no n to the minus 1/2 term in the cost, which is sort of because of the optimality principle. When you're at a minimizer, the first variation of the cost is 0 and the fluctuations are going to be described by processes with mean 0. So what is this linear quadratic Gaussian problem? So I'm going to state it here in sort of a standard form. And so the linear quadratic Gaussian problem is to minimize a quadratic cost function of the state and control variables, which looks like a running cost and a terminal cost, and subject to the linear stochastic differential equation for the state variable, and a similar linear stochastic differential equation for the observational variable, and a similar informational constraint that the fluctuation controls A should be a function of the history of the fluctuation of the observation. And this is exactly the problem that was solved by Kalman and Busey for continuous time, which is which I'll talk about in a second. And so here I'm just using some notation for all these matrices, but all these matrices are just coming from a second order Taylor expansion of the B, L, and G function. So the B was the expected drift, L is the running cost, and G is the terminal cost around S star and A star. And it includes the co-state as well, because you have this, right? So if you think of the second variation of a constrained optimization problem, you have this sort of bordered Hessian matrix, which involves the Lagrange multiplier, which is the role played by P star. And the diffusion processes theta and theta tilde are going to have the infinitesimal covariance given by the the infinitesimal covariance matrices, which we can find from the Markov transitions, evaluated at the mean S star and A star. And so it's important here, right? We don't have any derivatives of these because when we posed the problem originally, we saw that the covariance was already of order 1 over n. And so now we're looking at the square root of n, 1 over square root of n fluctuations. These are just going to show up. So next I'm going to show a little bit about what is the solution to this linear quadratic Gaussian problem, which is a very nice solution. So it breaks down into these two parts of the common filter, which the common filter, it solves this sort of Bayesian estimation problem of estimating the state variable, which you can think of as computing some sort of conditional expectation. And in fact, it does more than that, right? Because it solves for the entire distribution, which is going to be Gaussian with covariance matrix given by pi. So the common filtering procedure, so you can first compute this covariance matrix pi by solving a nonlinear matrix differential equation. And you can note it's quadratic, but here you always have solutions because the covariance matrix pi is always positive definite, and it's going to remain positive definite. And once you have this covariance matrix, you can determine the state estimate S hat using this sort of stochastic differential equation. So the equation for S hat, it kind of imitates the linear dynamics of the true state variable, and then has a correction term where you're looking at the deviations from the observations from what you expected. And this solves this for this conditional expectation in the Bayesian inference problem. And yeah, I want to mention, right, so the original work of Common was doing this in discrete time. Everything I'm talking about here, you can do also in discrete time. And the simulations I ran were really for a discrete time version of this, which is simple. And so the second part of the solution is to look at the dynamic programming principle. And so right in the dynamic programming principle, we're solving for a value function. And it turns out in this case, the value function is quadratic. And because it's quadratic, you can actually just solve for the Hessian matrix, and that will basically determine it. And the Hessian matrix solves this second matrix differential equation, often called a Riccati equation, which actually is very similar to the Common filter. And I would mention that in this case, it's not clear if we have solutions though, because we're going to look at some examples where, right, these matrices, like Q is the Hessian of the cost in the state variables, for instance, and it may not be positive definite. So and you can have you can have this diverge in finite time. Anyways, once you've solved for Z, you get a formula for the optimal control, which is a linear feedback control. So it's a linear transformation given explicitly here, multiplied by the common filter. And so you can see through this procedure, the optimal control for the linear quadratic problem incorporates the history of the observations through this S hat estimator. However, yeah. So the biggest computational challenge in computing these is really solving these matrix equations. And you can see there's a matrix inverse and there's a bunch of matrix multiplications. And I don't know much about how to efficiently compute these, but there's a huge amount of work that's been done as they're used all the time. So now I want to move on to the main result. So here's the main result in describing the fluctuations of our high-dimensional controlled Markov's process using this solution to the linear quadratic Gaussian problem. So we have a bunch of assumptions. So we're assuming that the initial condition is converging like a central limit theorem to some Gaussian S0. And so some of the matrices we need to be positive definite. We needed an inverse in the last slide. So this RT is the quadratic cost for the control variable, and it's this second derivative of the L along with the costate times the second derivative of the drifts. And so that will need to be positive definite. You can see a lot of, in the examples I'm giving, the B is linear in the control, so the second term drops out, and L is convex, so it's satisfied. And you need this theta tilde, which is coming from the covariance of the observational process, also to be positive. And finally, that the Riccati equation, the Vackers-Riccati equation, actually has a solution. Which again, there's a lot of things you could check to guarantee that is true. And under these conditions, then the fluctuations of the optimizers sigma n to the partial information Markov controlled process converge in distribution to the minimizer of the LQG problem. And as before, now we get a correction to the approximate optimal control by using our linear feedback relation with the estimation of the state. And the estimation of the state we can solve just as has been done in the Kalman filter, except applied with the actual data from our problem. So here, the observational process upsilon is being used as a correction for this state estimation sigma. So yeah, and so it's easy to implement numerically, and we'll incorporate the full history of observations in this approximate optimal control, which is now accurate to a next order accuracy in n. And so here's a picture of computing these back in the epidemic SIR model. So the dotted line is giving the mean field solution. And then I'm stating the true state for the simulation, which we don't know when we're deciding the control policy, as well as in the dashed line the estimated state, which we are calculating. And so the estimation is done based on looking at this time series of the positive tests per day. And you can see this kind of adapts to some deviation for this process that around day 30 or something, you start to get more infections, and eventually the estimation realizes that in the control policy adapts. But you can see also in the mean field, we kind of allow it to run free at the end time because of the boundary conditions. However, in this simulation, all the infections died out right before then, but you can see in a lot of simulations it will also grow at the end. So I want to talk about one more example, and this is an example of a phase transition occurring in this type of problem, and it's based on this famous, of course, Ising model from statistical physics. But we're going to just look at the very simple example, which is kind of the long-range interaction version of the Ising model. And so here we're going to have two states and two controls, and we're going to have a cost function where the cost of the control would be minimized around 1. So saying you have having an equal rate of transitioning from, say, sigma 0 to sigma 1 and sigma 1 back to sigma 0. But then we have a quadratic cost for the which is going to incentivize conformity, saying it's better if all of the population moves either to state sigma 1 or all the population moves to state sigma 0. And we can incorporate the information by saying that observations of being in either state sigma 0 or sigma 1 are generated at some constant rate. So when we analyze the mean field, okay, of course, you can, instead of looking at sigma 1 and sigma 0, you can just reduce to one dimension, which is the difference of the two, and solve for the steady state solution. So, right, this is just like a steady state solution to the Hamiltonian equations from the Pontryagin maximum principle. And you can always find this trivial solution where you have equal population in either category, and the control is just choosing the basically do nothing control. However, for certain parameter values, you get non-trivial solutions, which will be the minimizers. And you can solve for them exactly. And you see this similar sort of bifurcation diagram, phase transition diagram as in the Ising model, right? And in here, I'm plotting also the control and the non-trivial branches of the solution, where you can see, right, if you're in the state where not a lot of people are, you're going to want to choose your control highly to transition back. Whereas if you're in the preferred state, you want to choose your transition rates to be low. And so I think the nice thing about this is we can solve for everything exactly and look at the fluctuations. And if you remember from physics class, and you're at a critical phase transition, the fluctuations should diverge. So I want to see how that happens here. And so it doesn't happen with the information. So the covariance matrix for the state estimation doesn't depend on any of the doesn't depend on the cost. And of course, it gets smaller. As Q gets larger, it's the rate of observations is faster. However, when we look at the backwards Riccati equation for Z, we can see what happens at the phase transition. And so there's a steady state solution that exists in the regime where there's only one mean field solution. And in the other regime, that steady state solution doesn't exist anymore. And you can see that the solutions to this differential equation would diverge in finite amount of time. And what that means for the linear quadratic problem is there's going to be some control policies which achieve minus infinity cost, right? But of course, in this regime, that we're looking at this around a solution which is not a minimizer. So the theorem really doesn't apply. But however, at the critical point, the theorem does apply to describe the fluctuations, and you can solve for it all for the steady state solution. And so what we see is the linearized dynamics for that describe the fluctuations. So there's a sort of a attracting term, a linear term, and then the control ends up essentially canceling that. So the control, you can just solve it. It's 2 times s hat, and the s hat is the state estimation, which is going to remain close to s with covariance pi. S hat minus s is covariance pi. And so in the long time, the fluctuations are just going to grow like a Brownian motion. And so if you think about the ergodic limit, the ergodic limit exists when beta j is less than 1. And you can solve for the fluctuations there, but at the critical point, these fluctuations will diverge. And so on that note, I want to go back and talk about some of the more like general aspects of the problem and some of the sort of future questions. So specifically, so we made this major assumption of having long range interactions, which basically said we could write everything as functions of the empirical measure. Right, and so for the epidemic model, this was saying that basically every individual is interacting equally likely with every other individual in the population. And clearly this is a big approximation. And if we look at these sort of more short range interactions, there's many, well, challenges and interesting phenomena. So the examples are, well, we can extend this Ising game example to a sort of lattice Ising model and try to understand what happens there, where the interaction costs actually only depend on like the nearest neighbors on the lattice. And it's a much more difficult problem, of course. And And also in epidemiology, you can think about this as having, right, a network, looking at the network of contacts between individuals, and the information would be incorporated because you can use information about that network to reduce the infection rate between, right, locally on this sort of network. And so these would be interesting to look at. And one of the tools also, which is related, is machine learning. And so if you think about like these convolutional neural networks, they sort of learn information from like data sets of images by kind of learning these short range filters. So I think this is a really interesting approach to try to use for these partial information problems, see how if you can use neural networks in some way, like in the talk by Wainan A, but I don't know of any work that's done on the partial information problem from this perspective. And it's not clear how to do it because you have the time series of, time series of observations, which has to be taken into account. And also on the other side, right, you can analyze these sort of neural networks using some similar analysis as these, like in these limit laws, the scaling limits for like looking when the size of the neural network becomes large. And I've been working on this project, which doesn't fit into the framework of the problem I'm talking about, but is closely related. And so one other work that I've done on this kind of problem was this example of a one-dimensional mean field game, which we called the Dyson Game. And this was a mean field game with short range interaction costs. So I can mention almost all the mean field game literature is really making these assumptions of long range interactions. There's very little that addresses the short range interactions, but in here we looked at an example which had short range interaction costs. So the cost actually was like 1 over the distance to each other particle squared. And what we found is we could solve for the mean field limit, and we found that the information does affect the mean field limit. So contrary to the result, the general result, which occurs when you have long range interactions, because of the short range interactions, in fact, the leading order asymptotics do depend on the information, which is of course what we should expect because we see the importance of information in all of these examples, in all these applications. And in this problem, right, when you look at the fluctuations, well, they're non-Gaussian. They satisfy this other universality class, which is of course a very big topic. And when you look at the fluctuations of the control variable, they do not vanish in the limit. So you can solve for the mean of the control, but there's non-vanishing fluctuations, which is kind of where the change occurs because for the different information structures. And yeah, we use these open loop versus closed loop, which is different from what I was talking about here, but sort of related. All right, so I think I'll finish there. I wanted to just say that I appreciated all the hearing all the talks and everyone sharing their work. I thought I learned a lot, so thank you.
Okay, thanks for the really fascinating talk. Please jump in with questions from the audience if you have them. You can unmute yourself or type the questions into the box or raise your hand. Let me just ask a question to start things off. So I don't know a lot about about this field, but so you talked a bit about the Kalman filter at first, and this is sort of for the special case of like a linear time invariant system or something like this. And there's the more general sort of stochastic filtering framework for nonlinear dynamics. Is this something that you can address, or is this sort of only in the linear setting?
Yeah, so I think I don't know too much about this, but I can try to say something. I mean, so first off, there's no need for time invariance, right? In the problem we're looking at, we have a linear quadratic Gaussian problem. All of these matrices are depending on our mean field solution. They're depending on time. So time invariance isn't important for this, but the linear quadratic structure certainly is.
Okay.
And right, because otherwise you have no hope of having such a simple solution because things aren't going to remain Gaussian. They're going to be anything. But
sure,
that said, people apply this to all sorts of nonlinear settings. Even the example of the lunar landing, this is a nonlinear setting, and they applied Kalman filtering. So yes, it is applied widely in nonlinear settings. And I think to what degree that's rigorous, or just heuristic is unclear, but like, I think that kind of one of the things I'm doing in this talk is applying it rigorously in a nonlinear setting in this sort of asymptotic regime.
Yeah, in the nonlinear setting, there's it's what's called stochastic filtering, and there's like a rigorous formulation of this, but it's hard to solve, I think, because there's not such a simple equation like the Kalman filter gives you.
I mean, the basic problem is you'd want to know, given your history of observations, you'd want to know the distribution of the distribution of S, and it's not Markovian, so you can't even like write down a nice stochastic equation, differential equation for that or anything. Yeah, but I think that, I mean, there's been a number of talks also about this related problems to this sort of Bayesian inference as well, and so there's a lot of different techniques you can consider.
Okay, thanks. Yeah, are there any questions from the audience besides that? Okay, well, thanks for the nice talk. Let's move to the gather.town, which I'll put the link in the chat. And then don't forget that we have a talk tomorrow morning, our last talk of the workshop at 10:40. So if we don't see you in Gather Town, I hope to see you tomorrow morning. Let me try to get the link here. Okay, so here's the Gather Town link if you don't have it. Okay.